Today, we're not just telling a story. We're opening a cold case. We are conducting a forensic investigation into a ghost. Our subject is a material that became a legend, a metal so advanced for its time that when it vanished, people thought a magical secret had been lost. This is Damascus Steel, and its secrets we now know weren't written in a single formula, but were encoded in a fragile, globe-spanning ecosystem of specific ore, master artisans, and entire empires. So, using the tools of both a material scientist and a historian, we are going to reconstruct that lost world. Let's begin the investigation.
You know, this account from a medieval observer just perfectly captures the aesthetic heart of the legend. Listen to that language. The pattern is watered. This wasn't some design etched onto the surface. The pattern was an intrinsic, inseparable part of the steel itself, a shimmering, organic structure that seemed, well, alive. This watering, or damask as it came to be known, was the visual signature of a material that defied any simple explanation, and it gave the blades this powerful aura of the supernatural.
For centuries, really, the answer was believed to be magic. But today, looking back through the powerful lens of modern material science, we can actually reconstruct the science that was lost. We're going to peel back the layers of myth, of global trade, of geopolitics to get to the truth of this remarkable metal. This is a forensic deep dive into a lost technological tradition.
So, here's our plan of attack. Our investigation is going to proceed in 6 phases. First, we'll reconstruct the legend from the primary sources themselves. Then we'll decode the material at the atomic level. We're going to trace its journey across continents, diagnose the systemic collapse that made it vanish, look at modern attempts to bring it back, and finally uncover the profound lesson it teaches us about technology and history itself.
Okay, first things first, we have to understand the myth. The reputation of Damascus Steel wasn't built in a lab. It was forged on the battlefields of the Middle East and immortalized in chronicles. And these were not just tall tales from soldiers. Take, for example, the accounts of Usama ibn Munqidh, a 12th century Syrian diplomat who wrote about Frankish knights, the Crusaders, being absolutely astonished by the cutting power of the local blades. Then you have European chroniclers, like William of Tyre, who recorded the effectiveness of these weapons in the hands of Saladin's armies during the Third Crusade, and they wrote with this mixture of genuine fear and absolute awe. This wasn't objective reporting. This was politically charged myth-building. For the great Islamic powers, it was a symbol of their sophisticated civilization. For the Crusaders, it was a way to explain away their defeats and build up the mystique of their enemy. This is how the legend started. Stories of blades so sharp they could slice a silk scarf in half as it fell through the air, or so strong they could cleave a lesser European iron sword in two without even dulling. The very sight of that watery damask pattern became a weapon in itself, a tool of psychological warfare. It was a visual signal of a technology that seemed to border on magic, capable of demoralizing an opponent before a single blow was ever struck.
All right, now we move from the legend to the laboratory. We have to establish what Damascus steel actually is on a fundamental metallurgical level. And right away, we hit the first crucial forensic distinction, separating true Damascus steel from its many imitators. On the left, you have pattern-welded steel. This was the common European method, where a blacksmith physically layers different types of iron and steel, then heats, twists, and forge welds them together. The pattern you see is created by that physical lamination. But on the right, that's the real deal. This is a crucible steel, historically known as Wootz. And here, the pattern isn't layered on. It emerges from within a single, chemically uniform ingot of steel as it slowly cools from a molten state. The look can be similar, but how they are made is fundamentally different. Even the name Damascus is a bit of a historical misnomer. It most likely comes from the European Crusaders who first encountered these blades being sold in the great markets of Damascus. The city was a major hub for finishing and trading these weapons, but it wasn't necessarily where the raw steel itself was created.
The secret really begins at the atomic level with a very specific kind of steel called hyper-eutectoid steel. Now that's a technical term, but all it means is an iron-carbon alloy that has been supersaturated with carbon. Specifically, it contains more than 0.77% carbon by weight. For wood steel, it was often much higher, up to 1.5% or even more. And this excess carbon is the absolute key to everything. Because at that concentration, the iron matrix can't hold all of it in solution when it cools down. So the extra carbon has to go somewhere. It precipitates out, forming a unique, incredibly hard, and brittle iron carbide compound. And that compound is called cementite.
This simple chemical expression right here, this is the atomic event that underpins the entire legend. 3 atoms of iron, Fe, bond with 1 atom of carbon, C, to form iron carbide, or Fe₃C. This is cementite, It's a ceramic-like material, and it is incredibly hard. And those beautiful watery damask patterns you see on a blade, they are the macroscopic, visible evidence of this microscopic process. Inside the steel, you get this amazing composite-like microstructure. The bulk of the blade, the matrix, is a material metallurgist called perlite. It's a tough, resilient, finely layered mix of iron and cementite. This is what gives the blade its ability to bend without breaking. But running through this tougher matrix are distinct, visible bands of pure, hard cementite. Think of it like reinforced concrete. The perlite is the flexible concrete, and those cementite bands are the rigid steel rebar running through it. This combination is what gave the blades their legendary properties. The hard cementite provided an incredibly sharp, wear-resistant cutting edge, while the tougher perlite matrix gave the blade the resilience to withstand the shock of combat.
But here's the thing, the origin of this material isn't Syria. To find its source, we have to travel halfway around the world, to southern India, to ancient production sites in regions like Tamilakam and the Deccan Plateau. Here, the archaeometallurgical evidence from sites like Kudamannal and Tamil Nadu is undeniable. Excavations have unearthed the actual remains of specialized furnaces and, crucially, fragments of the high alumina clay crucibles, some still containing bits of slag and traces of high-carbon steel. These weren't just simple fire pits, they were advanced kilns, capable of reaching and holding temperatures over 1300 degrees Celsius. Inside these furnaces, sealed ceramic crucibles contained a precise recipe: raw wrought iron, carbon sources like wood or leaves, and glassy fluxes to pull out impurities. And that sealed environment was the key. It created a low oxygen or reducing atmosphere that allowed carbon to dissolve into the molten iron without just burning off. Even the ore they used was critical. We now know that specific Indian ore bodies contain trace amounts of elements like vanadium. These acted as catalysts, promoting the orderly formation of the fine carbide arrays that are essential to the final pattern. The final magical step in creating the ingot's hidden potential was a very slow, very controlled cooling process right there inside the crucible. And this process is governed by the fundamental physics of diffusion, described by the Arrhenius equation you see here. Let's break this down real quick. This equation tells us that the rate of diffusion, d, which is just how fast carbon atoms can move through the solid iron lattice, is exponentially dependent on temperature, T. So as the Wootz cake cools down, very, very slowly inside the crucible, the temperature drops. This gives the carbon atoms just enough energy, and more importantly, enough time, to migrate and cluster together, precipitating out of the iron solution. This isn't a random process. Guided by those trace vanadium atoms, they form the precursors to what will become the visible carbide bands. The legendary pattern of the final sword was literally written into the ingot's atomic structure during these first moments of cooling, all governed by the inescapable laws of thermodynamics.
So, the Wootz ingot is finally created. It contains that latent, beautiful pattern within it. But right now, it's just a rough, puck-shaped cake of steel. To become a legendary sword, it required an incredible journey across continents and the unique, unwritten genius of a master artisan. Let's trace this path. From the crucible sites in India, these Wootz ingots, literally worth more than their weight in gold, began a perilous journey. They traveled by sea, across the Indian Ocean to ports in the Persian Gulf, or they went overland on the grueling Silk Road. They passed through the control of powerful empires like the Abbasid Caliphate and later the Seljuk Empire, with each one levying taxes on this precious commodity. Persia, especially cities like Isfahan, became this crucial intermediary hub, not just for the trade of the ingots, but for the exchange of metallurgical knowledge. But this highlights a really critical distinction. The physical material, the ingot, was transported thousands of miles. The tacit knowledge of how to forge it, however, was highly localized, concentrated almost exclusively in the workshops of Syrian master smiths.
So here's where the true artistry comes in. The Syrian smiths possessed a deep empirical understanding of their material. They worked within an incredibly narrow thermomechanical window, somewhere between 700 and 900 degrees Celsius, and they judged these temperatures purely by the color of the glowing metal. They would gently forge the ingot, carefully deforming it to elongate the internal carbide structures into those beautiful flowing patterns. This was followed by something called subcritical annealing, repeated cycles of heating and cooling, all within that safe temperature window to refine the carbides. But the absolute #1 unbreakable rule was to never overheat the blade. If you heated it above about 1,000 degrees Celsius, those precious cementite bands would dissolve back into the iron matrix, permanently erasing the pattern and destroying the unique properties of the ingot. Without modern instruments, they were intuitively controlling phase transformations. They would heat the steel into its high-temperature, malleable austenite phase, or gamma Fe, where the iron crystals have a structure that can hold lots of carbon. Then they would cool it carefully. A rapid quench would shock the crystal structure into a hard, brittle, needle-like form called martensite, great for a cutting edge, but disastrous for the body of the blade. Their genius was in cooling it just right, preserving the tough pearlite while refining those beautiful carbide bands.
And today, modern analysis, using incredible tools like transmission electron microscopy, gives us a forensic breakdown of that final microstructure. At the nanoscale, we see these ultra-fine spheroidized cementite particles and these elongated carbide nanowires that trace the boundaries of the original iron crystals. This whole structure gave the blade a composite-like behavior, with a hardness of around 55 to 60 on the Rockwell C scale and a tensile strength up to 1.8 gigapascals, which is just truly exceptional for its time. Its legendary toughness came from its fracture resistance. Any microscopic crack that formed would be deflected and blunted when it hit the interfaces between the hard carbides and the softer pearlite, preventing the blade from shattering. Now, there were some studies in the early 2000s that proposed the existence of carbon nanotubes in the steel, but that hypothesis remains highly contested, and frankly, it's not necessary. The blade's incredible properties are fully explained by these more conventional, yet exquisitely controlled carbide structures.
Now, this knowledge, this entire tradition, it wasn't lost overnight in some big cataclysmic event. The decline, which happened mostly between the 18th and 19th centuries, was a slow, complex, and tragic unraveling of an entire technological system.
This technology's disappearance was really a death by a thousand cuts. It was this perfect storm of geopolitical and technological shifts. Around 1750, you see the decline of the Mughal Empire in India. This leads to political fragmentation, which disrupts the local production networks and the systems of patronage that supported the Wootz steelmakers for centuries. Then, by 1780, the expansion of the British East India Company begins to systematically reorganize all of South Asian trade, severing the ancient supply chains for those very specific ores. By 1800, European industrial steel, like Huntsman's crucible steel, starts to offer cheaper, more uniform alternatives. They didn't have the pattern, but they were consistent and affordable. And the final nail in the coffin? By 1850, the increasing dominance of firearms on the battlefield made elite swords strategically secondary. The military demand for these expensive, high-performance blades just collapsed.
So as you can see, the true cause wasn't just one thing. It was everything, all at once. The key Indian ore sources with those critical trace elements were either exhausted or became inaccessible. The colonial reorganization of trade routes completely severed the link between the Indian producers and the Syrian smiths. Mass-produced industrial steel from new processes like the Bessemer converter became economically dominant, and of course, military demand evaporated. And this leads us to the most crucial distinction we can make. It wasn't a single, secret recipe that was lost. It was an entire, fragile, transcontinental technological ecosystem that completely collapsed.
So, with the original tradition gone, a whole new quest began. The scientific mission to understand and replicate it. This started back in the 19th century with European scientists, like the pioneering metallographer Henry Clifton Sorby. In the 1860s, he was one of the first to study these blades under a microscope, confirming their unique internal structure, but he couldn't yet fully explain how it got there. It really wasn't until the late 20th century that modern metallurgists, armed with advanced equipment, were finally able to systematically reverse engineer the entire process.
The big breakthrough came from researchers like John Verhoeven, a metallurgist at Iowa State University, working with a master bladesmith named Alfred Pendray. Their work in the 1980s and 90s was groundbreaking. They demonstrated that by precisely controlling three key factors, a high carbon content between 1.3 and 1.6%, the presence of specific trace elements like vanadium, and a very strict thermal cycling schedule that mimicked what we think the ancient smiths were doing, the Wootz microstructure could be reliably reproduced. Their work proved once and for all that the secret was not some lost alchemical element or magic spell. It was disciplined, empirical control over known thermodynamic and kinetic principles. It was science.
And this comparison to modern metallurgy really puts the legend into its proper context. Sure, Damascus steel was incredibly hard for its time, measuring around 55 to 60 on the Rockwell C scale. But modern tool steels are harder, reaching up to 67 HRC. Its toughness was excellent for the era, but modern alloys are far tougher. And just look at the composition. Modern steels are complex alloys, intentionally designed with high concentrations of vanadium, chromium, molybdenum, and tungsten. These are designed to create a uniform, fine-grained carbide structure for predictable performance. Modern metallurgy prioritizes uniform isotropic properties over the beautiful visible patterns of Damascus steel. So the conclusion is clear. While it was the absolute apex of pre-industrial craft, its raw performance metrics are surpassed by modern engineered steels.
So, we've solved the metallurgical mystery.
We know how it was made, and we know why it disappeared. But in doing so, I think we have uncovered a deeper, more profound truth about the very nature of technology itself.
We have to understand that technology is not an isolated object. It's an emergent property of a complex, interconnected system. What was truly lost with Damascus Steel wasn't a recipe you could write on a scroll. It was the specific Indian ore with its unique trace element fingerprint. It was the tacit sensory knowledge of the smiths, judging heat by color, knowledge that can only be passed down through generations of apprentices. It was the specific transcontinental trade routes that connected those exact mines to those exact workshops. And it was the elite military demand that funded the entire expensive enterprise. The disappearance was a classic case of what historians call path dependence. Once industrial steelmaking became the dominant paradigm, all of the investment in infrastructure locked in a trajectory that made small-batch, artisanal crucible steel economically irrational, no matter how amazing it was.
And this right here is the ultimate lesson of Damascus Steel. We can remake the material in a laboratory. We can control all the variables and produce a piece of steel with the same beautiful microstructure. But we cannot reinstate the unique historical constellation of resources, institutions, trade networks, and artisanal knowledge that made it a living tradition for over 1,000 years. The metallurgy can be replicated, the history cannot.
And that leaves us with a final, provocative thought. The story of Damascus Steel isn't really about a lost secret, but about a historical rupture, the end of a specific, unbroken line of artisanal knowledge. It forces us to ask a bigger question about technology, about memory, and about the irreversible passage of time. When a technology's very existence is contingent on a world that has completely vanished, well, is lost even the right word? Or has it simply completed its history?